we're going to be building, physically building, we're going to simulator, construct a modeling process. So, going through all the intermediate steps, how it does affect, how does it decode, and how it does execute. So, that's what we're going to cover here. So, we've got our 3 building blocks, that's what we're having our simulation model of our processor. Control, data processing, and memory. Generally speaking, we sort of lump together the control and the data processing into one chip. So that is your processing still in the motherboard. The reason why we do that, so that's basically do that. So the same processor, we can have different amount of memory. Those are slots and thin slots in the motherboard. Obviously, you can put as much or less memory as I want, and also adjust the price of that computer. So generally speaking, the heart of the machine is one chip, the memory is the other. So we're going to be looking at how we build that. So it's been a computer. We've got these building blocks. So we've got the arithmetic logic. That will be our data processing. So our ALU, doing our adds, subtracts, multiplies if we have them, divides. Not all processors can do everything. So here I've sort of said multiplies and divides. But the simple processors will implement the multiply, divide, the more complex kind of mathematical operations at simpler adds and subtracts and shifts. So, but in that block there, that's where my data processing will be for. So the ALU. As we saw against that, when I'm doing that fetch, decode, execute cycle, when I do a fetch, I've got to put that instruction of fetch from memory in the computer, in the processor somewhere. So I've got to have some registers. So some storage inside that processor. So in the SAC simulator, we had the order register, or we had the program counter, which is the source control register. So you see, now got storage elements within the processor that are implementing that fetch, decode, execute cycle. If you have to remember something in the processor, it's got to be stored in a memory location within the processor, and we call those registers. So just fast memory locations within the processor. Separate to the memory location where I store my data and my instructions. Now, okay, I've got processing elements, so adds and subtracts, and my data, we have the multiply, multi-can registers, the accumulator, the SAC simulator, so lots of things that crunch numbers, lots of sources of data. We've got a root, the right bit of data, the right arithmetic unit within the machine. So that's what's defined by the instructions. So controlling that are the multiplexers. So they're like switches on a train track, routing the packets of data to where they need to go, and the results generated back to where they can be stored in memory. So routing information around the machine. Obviously, coordinating everything is the control. So that's what the instruction is kind of feeding. The instruction is interpreted and encoded by that logic, producing the right control signals to move the data around, figure the processing units, to fetch the operands, to do the calculations required. So that's what we're going to be building. They're the building blocks that we need to implement in this week's simulation. Okay, registers. So you've probably got a feeling there's 2 types of registers, 2 types of general purpose storage inside that process. Some are special purpose and some are general purpose. So the special purpose ones are the ones you don't have direct control over. So the things that do the fetch, decode, execute cycle. So, example, the program counter. So that was the source control register in the SAC simulator. That's a register inside the processor that points into memory to say, there's the instruction you need to execute. And normally it does increments. So you start off with perhaps address 10 stored in there, so I'll read instructions stored at address 10, and you read 11, 12, 13. As you go through that sequential program. You can't control that directly. You indirectly control that. You can't have an instruction that says set the program counter to a value. Instruction register as well. So what we've got there is I've got to fetch that instruction. Where did it go? It needs to be remembered. It needs to be stored in a register inside the machine. Again, you can't directly control that with your program. You indirectly control it, but not directly through an instruction. EXAC didn't really have this. We're a status register. So we need to that if we want to kind of look at how our calculations are behaving. Does the adding 2 numbers together, does it generate overflow? Will it fit within the processor's registers? Is the result generated as 0? Is it positive? Is it negative? So looking at how the results are changing inside the machine. And they're stored in another register called the program register. Obviously, as I calculate my program, I want, as a programmer, to generate intermediate results. So I'm generating instructions to do what my program needs to do. That will generate results. They need to be stored somewhere. In SAC, we only had the accumulator.
was a little bit inefficient. Because every time you generated results, you had to go there. If you want to generate another result, you had to farm that one out, push it out to memory, so you could free up the accumulator to be used by another instruction. But the accumulator, that one there, was always the destination for when you had to do the calculation and did a result of an instruction. Generally speaking, we have lots of general purpose temporary registers inside the processor. But we want to generate lots of different results and then combine them together with other instructions. So that's a very useful thing to have. Having just one is a little bit of a limitation. So as I said before, you do just have one general purpose register where your results will be going to, where your operand will be stored in, and we tend to call it the accumulator, just through tradition. So okay, there are memory elements in the machine. Some are kind of special purpose, and some are general purpose. You can control it as a program. So the multiplexer. So the thing that routes the traffic around the processor, we've actually built that in the hardware lab we did. When you did the bug crushing machine, you've actually built a multiplexer. And a multiplexer is just a kind of a digitally controlled switch. So here I've got 4 inputs, 1 output multiplexer. So I've got 4 sources of data, I've taken them from 4 general purpose registers, and I'm feeding them to the ALU. So I'm selecting any one of the 4 register values and passing it through to be processed by the ALU. Here's its truth table. So you can see the output X, this output here, can select between the inputs A, B, C, and D, depending upon what the inputs are, S0 and S1. So here are my inputs. Here are my control signals. So I've got obviously 4 inputs, so I've got 2 control bits, 2 to 3 and 4 states, 0 to 3, and depending on what that value is there, that will route the inputs to the outputs. So we go through, if you look at the slides, inside you can kind of conceptually think it's a switch. So you can see there I've got 0, 0 on the inputs, which control inputs S0 and S1. So I select 0 inputs, so input A. So again, if you look at it here, you've got 0 input is the first one. Going through the binary representations of the numbers, so 0, 1, 2, and 3, we'll select inputs 0, 1, 2, and 3. So 0, 0 on the input, select input 0, 0, 1, I select input 1, 1, 0, I select input 2, and 1, 1, I select input 3. So you can see here the control unit inside the machine can send us control signals to one of these multiplexers to route the traffic it wants to where it needs to go. As I said, that's what you built in the lab. So you look back at that lab where you did the cockroach kind of track, you built a circuit similar to this. So on the previous slide, you had a 4 input, 1 output multiplexer. So I can select 4 possible inputs and route it to the output. Here, this is what you built, a 2 input multiplexer. So you have 2 inputs A and B, so input 0 and input 1. So I need 2 inputs, so I don't need 1 control signal. So that control signal could be 0 or 1, routing the inputs to the output. So these are bit multiplexers. They select 1 bit. Obviously, your general purpose registers will have multiple bits. They've got an 8-bit register or 16-bit register. So if you need to route those bigger chunks of data, those bigger packets, all you do is just replicate these. So if I've got an 8-bit chunk of data, then for every bit, there'll be 1 of those. So basically, you can build them up in a hierarchical kind of way. Remember that the aim of these multiplexers is to kind of select the data and route it where it needs to go within the machine. So, what does this do? I've got a multiplexer. Its inputs are hard-coded to 1s and 0s. Here are my 2 control inputs, A and B, and here's my output, Z. So I've got 4 input multiplexer here, feeding the control signal effectively with a 2 input multiplexer. So that implements a logical function. Can you see what that logical function is?